Welcome to the session 2 of Unit 2 in Digital Signal Processing. In this session, we'll try to understand frequency domain sampling and reconstruction of discrete time signal. So, before we introduce with the discrete Fourier transform, let us try to establish a relationship between the Fourier transform and discrete Fourier transform. What I know is the definition of discrete time Fourier transform, that is x of omega is equal to summation x of n e raised to minus j omega n. So here x of omega is nothing but the discrete time Fourier transform of the discrete signal x of n. Now let us consider a discrete time signal x of n and its discrete time Fourier transform as shown below. So this what is my x of n, that is discrete time signal. So this discrete time signal is discrete time in nature, and it is also aperiodic in nature. So if I want to find out its frequency and domain representation, so as it is discrete time, it would be periodic in nature, and as it is in a periodic nature in the time domain, it would be continuous in nature. So this is what is the relation between the time domain signal and the frequency domain signal. If you have the time domain signal in the discrete time form, its frequency domain would be periodic one, and if you have suppose the time domain signal of aperiodic in nature, its frequency domain version would be a continuous nature. Okay, so this is what is the relation between the time domain and the frequency domain. So let me remove these annotations. So once I understood this x of n and x of omega and its nature, I can go further. Then what I have to do is I have to sample my x of omega and I have to denote it by x of k. So what I have written here is the sampled version of x of omega is denoted by x of k, and that is nothing but the DFT. Okay, so we'll sample it. So this x of omega, I have sampled it here, and after sampling means I have sampled it with the help of capital N number of samples in one period. So you can see here it is from 0, 1, 2, 3, 4 up to n minus 1. So I can sample one period with the help of capital N sample. So here I have sampled this x of omega and I have indicated that with x of k. Okay, so that x of k, why it is indicated by x of k, that we'll see further. And once I got this x of k, that is sampled version of this frequency spectrum, then I can have then I can take the inverse DTFT and I can have x cap of n. So the same thing I have written here, that after performing the inverse DFT, what you will get is a x cap of n, and you can see that this x cap of n and this x of n both are not same, while this x cap of n is nothing but the periodic extension of x of n. Means whatever the x of n I have, it is repeated after each period. So this is around 0, then I will get one more version at n, I will get one more version as 2n. Same is on the negative side, I will get one more version on minus n, one more version on minus 2n, and so on. So again you can observe here that again the same relation. What we can see, this x of k is, it is having a discrete it is in discrete version, and again it is periodic. If it is discrete version, the signal which I am getting here must be periodic, and if it is in periodic, I must get it in discrete form. Just 1 second. I must get this signal in discrete form. So that is what is the relation between these two transformations. Okay, so once I got this relation between xk and x cap of n, what we can conclude here is that this x cap of n is the periodic extension of x of n. So that is not the exact x of n, but it's a periodic extension. This x of n is repeated infinite number of times on the positive side as well as on the negative side. So that is what is the x cap of n. So here whatever the n I am considering here, that n is nothing but number of samples. So we are considering n samples in one cycle of x of omega. So this capital N denotes the number of samples of the input sequence and number of frequency points in the DFT output. So further, once we have finished with the sampling, that is we have considered x of n, then we have considered x of omega, we have sampled it, and here I have got the sampled signal. Once I got the sample signal, now I'll go towards its reconstruction. So now we'll go towards the reconstruction of discrete time signal. So we'll start again from the basics. That let us consider that an aperiodic discrete time signal x of n. So this is my x of n, which is a aperiodic discrete time signal, and its Fourier transform or DTFT I can find it out with the help of x of omega. That is x of omega is equal to summation of x of n e raised to minus j omega n, where x of omega is of periodic nature with the period 2 pi. So that we have seen in the previous session. Now let us sample this x of omega periodically at a spacing of delta omega radian. So we'll consider x of omega. Let us consider this is the x of omega for my reference, and I am sampling it at a spacing of delta omega. And what you consider here that its period is 2 pi. If its period is 2 pi, means this is from this point to this point. So this is the one period, that is 2 pi, and I have to consider capital N samples. So capital N samples means it would be 2 pi upon n, and this 2 pi n upon n is nothing but the spacing, that is delta omega, means spacing between the two adjacent samples, this much. So this much is nothing but what? Is nothing but the 2 pi by n. Understood? So let me use the cursor. Okay, so that is what I have written here. For simplicity, let us take n equidistant samples. So the samples should be equidistant in the interval 0 to 2 pi. So it is 0 to 2 pi with the spacing of delta omega equal to 2 pi by n as shown below. So this is what is the spacing, that is 2 pi by n in between the adjacent samples. So let us go further. Let us put w equal to 2 pi k upon n. Okay, so why this is 2 pi k upon n? Because it is x of omega, and it is what? It is x of k into delta w. So this k into delta w, how can I write x of k into delta w? Or you can write here x of delta w into k. Let me write it little proper. That is what? X of delta w into k, and what is delta w is 2 pi by n, that we have seen, 2 pi by n multiplied by k. So it is 2 pi by capital N k. Okay, and this is my x of omega. So this x of omega has converted into x of k into delta w, and this x of k into delta w is nothing but this, and this becomes now 2 pi by capital N k. So what is the change? The change is that the change here is this omega has become now 2 pi by capital N k. So we are putting omega equal to 2 pi by capital N into k in this equation 11.1. Okay. So further, now by substituting this, so this x of omega, this omega will be replaced with 2 pi k by n, so that is replaced over here. Summation of x of n e raised to minus j, this omega again will be replaced by this omega is replaced with 2 pi k by capital N, small n, and k runs from, as you can see that this k is running from 0 to n minus 1. Okay, because n samples I want, so if I will start counting the samples from 0, the last samples would be n minus 1. So, and this k indicates the sample number, so the k is running from 0, 1 up to n minus 1. So we'll go further now. So this summation is from minus mu to plus mu t, and I know that the samples, or I can collect the n samples in one summation. So what I can do, from minus mu to plus mu t I can split, and after splitting what I can do is I can collect the sample from sample number 0 to n minus 1, then I can collect the sample number capital N to 2n minus 1, or sample number 2n to 3n minus 1. Similarly on the left hand side, minus n to minus 1, or you can say here minus 2n to minus n plus minus n minus 1. Okay, so this complete summation minus infinity to plus infinity, I can split it, and I can have capital N number of samples in the each summation. So now we can observe that this I will get the infinite number of summations here. So if I am getting the infinite number of summations, I can write it further as I can write another summation here, that is L runs from minus mu to plus mu t, and this L I can put it here, that is Ln to Ln plus n minus 1. So this 0 is replaced with Ln, and this L runs from minus infinity to plus infinity. So I can write these all summations in one form in this way. Once I write all the summations in this way, I can change the index of inner summation, which is this Ln, from n to n minus Ln, and interchanging the order of summation. If I'll change the order of summation, if I'll change the index of inner summation, what will I get is, if I put here, if I'll change n to n minus Ln, means n to n minus Ln means what? N minus Ln minus Ln, so it will become 0, and if I put this here, what will I get is n minus 1, and I can change the summation. So this summation will come inside, will come inside, and this summation of n will go outside. So at the end, what I am getting is x of 2 pi k by capital N is equal to summation n runs from 0 to n minus 1, inner summation L runs from minus to plus mu to x of n minus Ln, bracket complete, and this e raised to minus j 2 pi k n, and k runs from 0 to n minus 1. Okay, let me clear all the annotations. So once I got this, we'll go further. I have just written this expression for our quick reference. Also, what I know is the xp of n is equal to summation of x of n minus Ln, because x of n is a periodic in nature. Okay, so x of n minus capital N, x of n minus capital 2n, x of n minus capital 3n, everything would be equal to what? Xp of n. So I can write this as xp of n is equal to summation of x of n minus Ln, L runs from minus mu to plus mu t, and it is obtained because of the periodic repetition of x of n. So as a result, this xp of n from this 12.2, I can as this xp of n is having a periodic nature, I can write it in terms of the Fourier series form. So this xp of n I can write in terms of what? Fourier series form. So if I write it in terms of Fourier series form, what you will get is xp of n is equal to summation. I can use Fourier series and I can write it in this way: summation k runs from 0 to n minus 1 ck e raised to j 2 pi k n, n runs from 0 to n minus 1. So where again, if it is Fourier series, I can write down the expression for ck 1 by n summation xp of n e raised to minus j 2 pi k n by capital N, k runs from 0 to n minus 1. Now if we'll consider these two expressions here, 12.1 and 12.2, then this summation is actually here. So this I can replace with what? xp of n. Okay, so if I'll replace this with xp of n, so this x of 2 pi by n k will become, the summation will remain as it is. This complete summation x of n minus ln will be replaced with xp of n, and this e raised to minus j 2 pi k by capital N n, and k runs from 0 to n minus 1. Now let us compare 12.4 and 12.5. If we compare this, what you can write is for ck. Now you can see here, let me use another color. Yes, we'll use this much. So ck, so this is summation n runs from 0 to n minus 1 xp of n, and this complete, both are same. So ultimately my ck will become what? 1 minus n into x of 2 pi k by capital N, k runs from 0 to n minus 1. Okay, now we can again compare this 12.6 and 12.3. So if we compare this, so we can see here this value of ck, I can put it here. So I can write xp of n, what color I can use now? Okay, I can use this xp of n equation here. So xp of n is equal to what? This I can write here 1 by n x of this much. That value of ck I can write here. So I can write 1 by n summation k runs from 0 to n minus 1 as it is. ck will be replaced with x of 2 pi k n, 1 by n we have taken already, and then e raised to plus j 2 pi k n by capital N for n runs from 0 to n minus 1. So this is what is the let me clear all the notations. This is what is the equation we got it for xp of n. Now the same xp of n we will bring it further, and now you can see here that the relationship obtained in the above equation provides the reconstruction of xp of n from x of omega. Yeah, so this is nothing but x of omega. If you remember, this is nothing but, sorry, this is nothing but x of omega, and this is nothing but the xp of n. Okay, so it provides the reconstruction of xp of n from the x of omega. Okay, but it does not mean that it can cover x of n. okay, because xp of n is a periodic extension of x of n. So x of n can be recovered only if there is no aliasing. Okay, what I have written here is the xp of n I have written in terms of x of omega. So what you can say that the above equation gives me the reconstruction of xp of n from the x of omega. Okay, so I can reconstruct xp of n from this x of omega, but it would be true only if my x of n can be recovered if there is no aliasing. So just we'll try to understand the aliasing. For that purpose we'll consider a particular situation. So let us consider a finite duration sequence x of n. So this is my x of n, and this x of n is having the its length as L. So it will have L number of samples. Now we'll consider a case where capital N is greater than or equal to L. If this is the case, so whatever the xp of n is there, if I am considering that the capital N is greater than L, means this is my capital N number of samples, and this is my length of my original sequence. So if it is the case, what I can do is I can have a filter or window, and I can take out this portion and I can name it as x of n. Means I can filter out this part and I can recover x of n when n is greater than L. So that is the necessary condition, that if n is greater than or equal to L, then I can filter out and the specified or desired part, and I can recover back my x of n. So the same thing I have written here, that xp of n is equal to x of n if for small n in between 0 to n minus 1. So in this case x of n can be recovered from the xp of n. Okay, so let us go towards the next case, that is n less than L. So let us clear all the annotations, and for n less than L we will have xp of n one more time. So this is the next xp of n for this n less than L case. So you can observe here, we will take the annotations. So you can observe that this is the number of samples n, and this you can refer it as n, and it is what is written here is that L is greater than capital N. This is the L. So in this case you cannot separate out the L samples from this spectrum of xp of n. Okay, so you cannot separate out the capital L samples, because this is the first period, sorry, x second, this is the first cycle, and let's another pane, this is the second cycle. Okay, so in between these two cycle there is a overlapping, this overlapping, and because of this overlapping I cannot separate out the original signal from the xp of n. Okay, so in this case, that's why this x of n cannot be recovered from the xp of n. Therefore we can conclude that the spectrum of a periodic discrete time signal with a finite duration L can be recovered from its samples at frequencies wk equal to 2 pi k by capital N if and only if n is greater than or equal to L. So in this way, from the xp of n, we can find x of n. From this xp of n, we can find x of n, provided capital N is greater than or equal to L. And once I got this x of n, I can find out x of omega. Okay, so that's it for this session.